Hello everyone and welcome to another video. Today we'll start topic 5, the periodic table. The periodic table is how the elements are arranged according to the increase in their proton number. As you can see, this is the periodic table right here. In the periodic table we start with hydrogen. Here it has a proton number of 1, then helium with a proton number of 2, lithium 3, beryllium 4, boron 5, and so on. So elements are arranged according to the increase in their proton numbers. You can tell from this arrangement that there are no missing elements, or there are no elements to be yet discovered, because there is a continuous arrangement of the elements according to the increase in their proton number. So the increase is continuous, so there are no gaps within the periodic table. Elements in the periodic table are arranged in two different ways. The vertical arrangement right here is called a group, while the horizontal arrangement is called a period. Here we have the group number, which indicates the valency electrons, meaning that in the same group, elements have the same number of valency electrons. So in group 1, for example, all of these elements have one electron in their outermost shell. Just to make sure, we have lithium 3, 2, 1, that is electronic configuration, sodium right below it, 11, 2, 8, 1, and so on. So each of the elements in the same group have the same number of valency electrons. In the period, elements in the same period have the same number of energy shells. So for example, here we have lithium and beryllium and boron. Let's check these out. Lithium has the electronic configuration 2, 1. Beryllium has the electronic configuration 2, 2, and boron has the electronic configuration 2, 3. So we notice that all of these elements have two energy shells occupied with electrons. That's because they are in the same period. That's period 2, which means that there are two energy levels occupied with electrons. I prefer to arrange the periods from this side actually, other than from the left side. That's because if we look here, we have helium and hydrogen. These two are in period 1. Then we have neon in period 2, argon in period 3, krypton 4, xenon 5, radon 6, and here we have the last period, which has francium and radium and the actinoids, all of them. Below the periodic table we have these two periods, the lanthanides and the actinides. These two were originally placed in here in the middle of the periodic table, but because placing them there will just make the periodic table way too long, so they had to separate them below the periodic table. The lanthanides are the elements right after the lanthanum, and the actinides are the elements right after the actinium, hence their names. And of course the lanthanides are in group 6, because if you look at their place, they are right here, that's group 6, and the actinides are in group 7. So don't get confused by these ones. There is another way elements are arranged or categorized in the periodic table. That is, elements can be arranged according to their metallic properties into metals and nonmetals, and right in between these two there is a category called metalloids, which we'll be talking about later on. Right? Metals can be further classified into group 1 and 2 metals and the transition metals. Or the transition metals, yeah. Right? Let's apply that on the periodic table. These are groups 1 and 2. So these are the group 1 and 2 metals. These are the transition metals right here, including also these, the actinides and the lanthanides. Right here, starting from group 4, here we have the non-metals. And we have this zigzag line right here, which separates the metals from the non-metals. So this is the heavy zigzag line that separates the metals from the non-metals. Here we have boron, silicon and germanium, arsenic, antimony, and all of these elements are called the metalloids. All right, let me just draw them in or identify them in another color. Here, boron, silicon and germanium, arsenic, antimony and bismuth, tellurium and polonium. All of these are metalloids. So what are metalloids? Metalloids are metals in between metals and non-metals, or they are elements, sorry, in between metals and non-metals. Their properties have some of these from metals and others from metalloids. They are also called semi-conductors. So now we have talked about the arrangement of elements in the periodic table. We're going to talk about metals and non-metals and the transition elements in greater details. But before we do that, let's talk about the metallic property. As we mentioned, these are metals. So going from right, just let me delete all of that. Okay, going from left to right, like that. The metallic property decreases because if you think about it, these are all metals. Right here, these are all non-metals. Here we have the transition metals, so in between this distance between the metals and the non-metals, the metallic property decreases. And right here we have the non-metals, so the non-metallic property increases, going from left to right. Now, within the group, for the metals, the metallic property increases. Right here, the metallic property increases. So if we are comparing lithium, sodium, potassium, the highest metallic property will be for potassium. Potassium will be higher in metallic property than sodium, and sodium will be higher than lithium. Now in the non-metals, going down the group, the non-metallic property decreases, meaning that the highest non-metal of the non-metallic property is fluorine. Fluorine is the strongest non-metal of them all. So chlorine has a higher non-metallic property than bromine, and bromine has a higher non-metallic property than iodine. Okay. Now we're going to talk about metals and non-metals in greater details. The alkaline properties and acidic properties, we'll talk about them later in the acids and bases. As for the artificial elements, these are elements that were synthetically made in the lab. They are radioactive and they don't occur in nature. They decay most of the time, forming other elements, and they are present down here. Most of the lanthanides and actinides are synthesized. All right. Now we'll talk about the differences in between metals and non-metals before we dive in each of the groups. We'll be studying Group 1 and Group 7, and then we'll talk about the transition metals. Starting with the physical properties. For metals, metals have high melting and boiling points, and they are solids at room temperature, except for group 1 metals. The exceptions are very important because in most cases in the O level for year 10 students, they are asked to explain why group 1 metals are not ideal or typical, metals. They're not usual metals. That's because of these exceptions. In general, metals have high melting and boiling points and they are solids at room temperature. But group 1 metals have low melting and boiling points. And another exception is that mercury is a liquid at room temperature. Mercury is the only liquid metal at room temperature. Metals are good conductors of heat and electricity. There are no exceptions here. Metals are hard in general, except for group 1. Group 1 metals are soft. Metals have high densities, exception group 1. They have low densities, as we will see in a few minutes. Metals are malleable, which means that they can have their shape changed by hammering, and they are ductile, which means that they can be pulled into wires. Always think of copper. Copper is used in making electrical wires. It's a transition metal, so it's a metal. It follows the general rules. It's ductile, so it can be pulled into wires. They are sonorous and they are shiny. All metals are shiny. So the important part in here is the exceptions for group 1 metals. So group 1 metals have low melting points and boiling points. That's the first point. They have low densities, and they are soft. They are soft. Okay. Now let's talk about non-metals. Non-metals have low melting points and boiling points. Actually, most of them are gases, so they have low melting and boiling points. Exceptions, the macromolecular structures, carbon, silicon, boron, and germanium, these four macromolecular structures, as we've discussed before, carbon can form graphite and diamond. These have very high melting and boiling points. Silicon can form silicon dioxide or silica, which also has very high melting and boiling points. Boron and germanium are the same. They can form macromolecular structures. So these are the exceptions for this rule. Nonmetals are poor conductors, of course, because they form covalent compounds. They are made of uncharged molecules, so there are no freely moving electrons. An exception for that is graphite. As we mentioned, graphite is capable of conducting electricity because of the freely moving electrons in between the layers. Nonmetals are soft, except for the nonmetals with macromolecular structures like carbon, silicon, boron, and germanium. All nonmetals have low densities. They are brittle, which means that they do not change their shape, but they break. If you try to hammer some graphite, it will just form a powder. It will not form a wire and it will not change its shape. Except, of course, for diamond. Diamond isn't brittle. It's actually the hardest metal known, element known. They're not sonorous and they have a dull surface, which means that they do not reflect light. That's the meaning of shiny. Shiny means that the metal reflect light, right? Non-metals have a dull surface, meaning that they do not reflect light. Except for graphite, iodine, and diamond. Iodine, of course, in its solid state. If you look at iodine's solid state, it can reflect light. Diamond, of course, reflects light, and so does graphite. Now let's talk about the chemical differences, but before we go into the chemical differences. For year 9 students, yeah, they may be asked to compare in between metals and non-metals. But for year 10 students, they are usually asked to compare between group 1 metals and transition metals. All right. So if you're asked to compare between sodium and copper, for example, or between potassium and iron, of course you're gonna have to mention these three ones or these three properties because these are the main differences or the exceptional characteristics that group 1 metals have. So sodium has low melting point and boiling point, while iron will be having a high melting and boiling point. Sodium has low density, iron has a high density. Sodium is soft while iron is hard. The other properties are common properties in between these two, so you can't use them to differentiate between group 1 metals and transition metals. Now let's talk about the chemical properties. The chemical properties are actually determined, if we go back to the periodic table, the chemical properties are determined through the group number. Why they are determined through the group number? Because the group number indicates the valency electrons, and the valency electrons determine the behavior of the element in a chemical reaction, whether it will lose electrons or gain electrons or share electrons, which determines whether it's a metal or a non-metal. So back to the chemical differences. As for the electronic distribution, metals have 1, 2, or 3 valency electrons. They tend to lose electrons forming cations or positive ions. Nonmetals have 4, 5, 6, or 7 electrons. They tend to gain electrons forming anions or negative ions. They can also share electron pairs, forming covalent bonds. The type of compounds, metals form ionic compounds, and we've talked about these in greater details. You can check the video on them from the playlist. They form ionic compounds with non-metals. They are formed due to the electrostatic attraction forces between the positive ions and the negative ions in the crystalline lattice. The non-metals form covalent compounds with other non-metals. The reaction with acids. Metals do react with diluted acids, forming salt and hydrogen. We'll talk about the equations in a few minutes. Nonmetals do not react with acids, but you can't stop here. You can't stop your answer here in the comparison. It will be wrong. Nonmetals do not react with acids to give a salt and hydrogen. They actually give other compounds or give other products. So just to clarify, nonmetals do react with acids, but they do not give salt and hydrogen. They give different products. Now let's talk about group 1 metals or the alkali metals. Why are they called alkali metals? Because they react with water, forming alkalis. So what are alkalis? Alkalis are the metal hydroxides. They are bases, which means that their pH is between 12 and 14. We'll talk about the pH and the acids and bases later. Now to the physical properties. Down the group, the alkali metals are not typical metals, and we've already talked about the differences in their physical properties. First of all, they are monoatomic, which means that they exist as a single atom. For example, sodium exists as just sodium, potassium, lithium, and so on. They are soft, and their softness increases, which means that lithium is the hardest. If we go back to the periodic table right here, their softness increases, meaning that sodium is softer than lithium and potassium is softer than sodium and so on. So lithium is the hardest of group 1 alkali metals. Their melting and boiling points decrease down the group. Their densities increase. Sodium and potassium are out of step. What does that mean? If we look here, we have the densities of some of the group 1 metals: lithium, sodium, potassium, rubidium, and cesium. The density here is 0.53, 0.97, 0.86, which is really strange. I mean, it should be increasing, and then 1.53 and 1.88. These are correct, and these are correct because the density is increasing. But for potassium, it's really strange. It's 0.86. It should be increasing like 1.3 or 1.2, something like that. That's why sodium and potassium are out of step, as you can hear. But which one is actually the odd one? Potassium is the odd one, right? How did we know that potassium is the odd one? Simply, if you consider the differences in between sodium and lithium, and then you consider the differences between cesium and rubidium, they will be very, very close to each other, which means that these are in the correct order and these are in the correct order, but the differences in between sodium and potassium, they are very wrong. Actually, potassium should be increasing, not decreasing. So we take rubidium and cesium as a reference and we compare it to the difference between lithium and sodium, and they are actually the same difference, meaning that potassium is the odd one. The potassium has the odd density. As you can see here, lithium, sodium, and potassium, these have a density lower than less than 1, which means that they all of these three float above water because the density of water is 1 gram centimeter cube. They are conductors, good conductors of heat and electricity, just like all metals. They have a shiny surface. Again, their softness increases. As you can see, lithium is soft, but it's harder than the rest of the group 1 metals. Okay, so you need to pay very good attention to these two properties, the density and the melting and boiling point decrease, and the softness. These three properties are very, very, very important because these are the differences between um, the group 1 alkali metals and the other metals. Now to the chemical properties. They are monovalent, and you need to pay attention that there is a huge difference between monovalent and monoatomic. Monovalent means that these elements in chemical reaction participate by losing a single electron. They have a single fixed valency. Because when you look at transition metals, no, they have many valencies actually. They can participate in chemical reactions by losing more than just one electron. We will not be studying that characteristic in O level, but you will be studying it in the AS. Sodium, for example, has the electronic configuration 281. It loses one electron, forming a sodium ion or a cation. So it has a fixed valency of 1, so it's a monovalent. Monoatomic, on the other hand, means that the atom in nature exists as a single atom, right? A diatomic molecule like hydrogen, for example, exists as two atoms bonded together, as we will talk about in the non-metals. So that's the difference between monoatomic and diatomic. So don't confuse it for monoatomic and monovalent. Right? An atom can be diatomic but also monovalent. The monovalent thing talks about the valency, right? The amount of electrons used in sharing. Are you using or sharing with a fixed number of electrons, or are you capable of sharing with more than one electron? Just to explain this further, aluminium has the electronic configuration of 283. It's also monovalent because it loses 3 electrons, forming an aluminium ion. Right? So in chemical reactions, it's capable of losing 3 electrons. It always loses 3 electrons. Manganese, for example, it's a transition metal. It can lose or participate in chemical reaction by losing 1 electron, 2 electrons, 3 electrons, 4 electrons, all the way up to 7 electrons. So you can't say that manganese is monovalent, right? Because it can participate in so many different ways. While aluminium, calcium, group 1 and 2 metals in general, and halogens, they are all monovalent because the way they participate in chemical reactions is fixed, right? So that's what monovalent means. Let's just delete that because aluminium is not an alkali metal. It's not a group 1 metal. All right. Their activity increases down the group, as we've mentioned, because the number of energy levels increases. The atomic radius increases, so the attraction forces between the nucleus and the valency electrons decrease, making it easier to lose electrons. As you can see, this is lithium, 2, 1, sodium, 2, 8, 1, potassium, 2, 8, 8, 1. As you can see, the distance in between the nucleus and the last energy shell keeps increasing. So the attraction forces between that nucleus and that very far electron keeps getting weaker, which means that losing that electron is much, much easier as we go down the group. Since they are highly reactive, they are stored under oil or kerosene. You can't just leave a piece of sodium out there in the open air. It will react with the oxygen and the vapor in the air, and there will be a chemical reaction, probably leading to explosions and formation of hydrogen, which is actually flammable, and we'll talk about that. So they must be stored under oil or kerosene to prevent them from reacting, because they are very, very reactive. This part is very, very important. They form white solids, compounds that dissolve in water, forming colorless solutions. So if you are ever asked about the color of KBr solution, NaCl solution, Li lithium iodide solution, all of these are colorless solutions, right? So always remember, um, the solids themselves in their solid state, the solid is white, the solution is colorless. How would you differentiate if he's asking about a solution or a solid? If the compound is KBr with a symbol state of S, that's a solid, it's white. If it's KBr with a symbol state of aqueous, that's a solution, means that the KBr was dissolved in water, forming a colorless solution. Okay, now we'll talk about the reactions. These are the equations. From now on, we'll be taking chemical equations, so try to pick up the balance, right? First of all, we have the reaction with water. First of all, we have the reaction with water. They form metal hydroxide, as we've mentioned, or the alkalis, and hydrogen gas evolved. For example, here we have lithium plus water gives us the alkali, lithium hydroxide, and hydrogen gas evolves. These reactions are exothermic, meaning that they release energy. So if you are performing this reaction in a beaker, the beaker will be getting hot, right? And these reactions become explosive as we go down the group because the activity or the reactivity of the metals increases, as we will see. For example, here we have lithium. It readily reacts. These keywords are very, very, very important. The lithium readily reacts. The sodium vigorously reacts. Potassium is violent. Rubidium is explosive. So as you can see, we are going down the group in here. The reactivity of the metals increases, and the violence or the strength of the reaction increases as well. Lithium floats because its density, as we mentioned, is less than water, so does sodium and potassium. Lithium melts and forms bubbles. Right? The amount of bubbles isn't that much, but they are present. They are bubbles of hydrogen, of course, bubbles of hydrogen gas. Sodium shuts across the water surface like fireworks. When you blow off fireworks, they shoot across the sky. It's the same thing here with sodium. There's also fizzing, and it may catch fire. And if it did catch fire, its fire will be golden yellow. Potassium, there is effervescence, which means that the amount of bubbles is much, much more than lithium and sodium. There's a hissing sound, and it definitely catches fire. Okay, And when it catches fire, the flame fire is lilac flame. It's a purple flame. Rubidium is explosive, right? So you can uh, understand from that that their activity increases and the violence of the reaction increases. Again, the keywords are very, very important. There are precautions to be taken while performing this reaction between an alkali metal and um, water. You must always use eye goggles to prevent your eyes. It should be behind a screen or a flame cupboard because they are flammable, they are exothermic, they release energy. We of course use small pieces of the metals in a large amount of cold water, right, to reduce the effect of the heat that will be formed, because again it's an exothermic reaction. We don't want the reaction or make it to explode, right? And of course, in a lab or in the schools, we do not use rubidium. We use something like sodium, for example, to show the effervescence, or sorry, to show the bubbles of the hydrogen, and we use lithium as well, maybe potassium, but that's it. You can't use rubidium. It's so reactive, it will be exploding. All metals are reducing agents. We will talk about that at the end of the topic. The reducing agents, the oxidizing agents, and the redox reactions, all of that, we'll talk about it in the end of the topic. Now we have the reaction with chlorine. Heating the three metals and plunging them in a gas jar of chlorine. That's how the reaction is actually done. You're provided with a gas jar that has chlorine gas in it, and you bring, using a spatula, you bring in the metal. It should be hot, really hot, and you put it in the gas jar, and the reaction happens. Here we have sodium, it's a solid. Chlorine is a gas, and we have sodium chloride, of course, that's table salt, it's solid. um, Alright, they burn brightly, forming chlorides. Now we have the reaction with oxygen. Heating the three metals and plunging them in a gas jar of oxygen, they burn fiercely, forming oxides. So sodium, for example, plus oxygen, we have sodium oxide, right? Alkali metals have very important uses. Lithium is used in batteries like mobile batteries, laptop batteries, and so on. Sodium is used in street lamps and in car lamps as well, because it gives very, very bright light. Potassium is used in making fertilizers to improve the quality of the soil. Okay, so that was it for metals, or alkali metals, group 1 metals. Now let's talk about group 7 nonmetals, or the halogens. Their physical properties, they are nonmetals. They are diatomic, meaning that they are present in nature as molecules, two atoms bonded together. For example, chlorine exists as two chlorine atoms bonded together, like that, right? So these are diatomic. They are poisonous. That's why they are used as antiseptics. They kill germs and bacteria, so we use them as antiseptics because they are poisonous. Their melting point, boiling point, and density increase as we go down the group, as you can see here. Here we have fluorine, chlorine, bromine, and iodine. Gas, liquid, and then a solid, meaning that their densities is increasing and their boiling points are increasing as well, as you can see from here. Of course, the numbers aren't to be memorized. I'm just showing you that the boiling points are increasing as we go down the group. They are bad conductors of heat and electricity, of course, and their color is getting darker. Let's see. Fluorine is a pale yellow gas, and the colors are very, very, very important. Chlorine is a yellowish green gas. Bromine is a reddish brown liquid, and iodine is a black solid. So as you can see, the colors are getting darker. Now let's talk about the chemical properties. Oxidizing agents, as I said, we'll talk about them in the redox in the end of the topic. They are monovalent. Again, they are diatomic, meaning that they exist as two atoms bonded together, but they are monovalent because in chemical reactions they participate in the same way by gaining a single electron. Chlorine is 287. In a chemical reaction, it gains one electron, forming a chlorine ion or an anion. It's a negative ion, and we've talked about why these are negative because the amount of negatively charged electrons is greater than the amount of positively charged protons. They react with metals, forming salts. Sodium and chlorine is NaCl. Iron and bromine forms iron bromide. Aluminium and iodine forms aluminium iodide. The chemical reactivity decreases down the group. So the most reactive nonmetal is fluorine, and for a matter of fact, it's the strongest nonmetal of them all. Okay. A halogen will displace a less reactive one from a solution of its halides. If we want to arrange the nonmetals, or sorry, the halogens according to their reactivity, it will be like that: fluorine, chlorine, bromine, and iodine. Right? As we go down, their reactivity decreases. Right? So, if fluorine is more reactive than chlorine, then fluorine will just replace chlorine in its salt. For example, here we have chlorine and we have potassium bromide, right? Chlorine is more reactive than bromine, which means that this reaction will happen and chlorine will replace the bromine, and the bromine will be kicked out as a liquid right here, right? As a bromine um, atom, it will be replaced by the chlorine. Here we have chlorine and potassium iodide. From here we can tell that chlorine is more reactive than iodine, which means that chlorine will replace the iodine and the iodine will be kicked out, like that. Same for bromine and sodium iodide. Now, if you think about iodine and sodium bromide, is iodine more reactive than bromine? No, iodine is below bromine, meaning that iodine is less reactive. So iodine cannot replace bromine, so no reaction will happen. As we've mentioned, all group 1 metal halides are colorless. These are called a metal halide. KBr is formed by a metal reacting with a halogen, so that's a metal halide. They are colorless. In their solutions are colorless and they are white solids. This type of reaction is displacement and redox reaction. For now, I just need you to understand that a redox reaction, one of the types of redox reactions is displacement. When you replace one atom with another, that's a displacement, and it's a type of redox reaction, and I will explain it in the redox reactions at the end of this topic. I think that's enough for today's video. Thank you so much for watching. Don't forget to like the video, share it with your friends, subscribe to the channel. If you have any questions, leave them in the comment section below. The notes and classified are on the Telegram group. You can reach it from the video link in the video description. And I'll see you in the next video. Take care.